G'day guys, I've got another math puzzle for you. What is the largest radius of a ball that can rest at the base of a parabolic dish given by the equation y is equal to x squared? So to make that a little bit clearer for you, this ball, for example, has a radius which is too large because it gets stuck in this parabola. However, the radius of this ball is good enough because it can rest at the base of this parabola just here. Okay, that's the problem. Have a shot at this yourself first and then come back when you're done. Okay, well, you might be tempted to try and solve this through a calculus heavy route, but I assure you there's an easier way, and it begins by considering the equations of both the parabola and the circle. So let's first begin by drawing our parabola just here. This right here is our parabola, and it's given by the equation y is equal to x squared, like this. Now let's consider the equation of a circle which does rest at the base of this parabola. And in general, a circle which does actually touch the origin like that can look like this. Right? So this is the equation of a circle which does touch the origin just here. And the equation of this circle is y minus r squared plus x squared is equal to r squared. Notice it's just the equation of a circle shifted up r units. Right? And what I'm going to do now is I'm going to consider where does this circle and where does this parabola intercept. And the way we do that is by setting these two equations equal to each other. So let's do that. This will be y minus r squared plus, and instead of writing x squared, we're going to write y here. So we're going to write this as y, and that's going to be equal to r squared like this. Now we need to go through the algebra here to solve for y to figure out where they intercept. So let's do that. This will be y squared minus 2ry plus r squared plus y is going to be equal to r squared like this. And we notice some interesting cancellation. We notice there's an r squared which will cancel out like this. And of course we can also factor out a y here. We can write this as y times by y minus 2r plus 1 is going to be equal to 0. Okay? So in fact, what this equation now tells us is there's 2 points where there's 2 y coordinates at which the parabola and the circle intercept. They intercept at a point here, 0, and they also intercept at a y coordinate here, which is given by this. So let's go down that route. We know that one solution is y is equal to 0, and we know the other solution is y minus 2r plus 1 is equal to 0. In other words, y is equal to 2r minus 1. That's basically this y coordinate just here. That's where this parabola and circle intercept, right? Now, you might be thinking, well, what's the point in finding out where this parabola and bowl intercept? I mean, it seems like we're no closer to solving the puzzle, right? But in fact, we are, because we can solve for the case where the interception of this parabola and this circle up here is actually equal to 0. Right? Just imagine, if we slowly decrease the radius of this bowl, then we're going to be decreasing the y value at which they intercept. So just imagine bringing this dotted line down closer and closer and closer by shrinking this bowl until it touches just here. And that's the point at which the bowl rests inside the parabola without intercepting its sides. So what we're doing now is we're solving for y is equal to 0 in this equation. And then we're going to get 0 is equal to 2r minus 1. And of course, from this you can tell that r is going to be equal to a half. There we go. That is the largest possible radius of a bowl that can fit inside this parabola. Of course, anything less than that but greater than 0 can still work. I hope that made sense, guys, and I hope you really enjoyed that problem. Just so you know, I also do videos in engineering, vibrations, dynamics, and statics. So check out my website too if you like. Cheers.